of these online lectures related to landslides in highway construction. Today, as usually, I would like to start with a with open possible discussion about the topic we talk about so far. Topic 1, 2, and 3, first three parts. If you have something to discuss about, something to ask about, something to suggest, please feel free to to do it. If there's something maybe we skipped too fast or we didn't explain, or even if you have some questions regarding the assignment I sent you as a part of this course. If there's no questions and discussion, I'll start with this last topic named computer software for identification of failure mechanism and design of remediation measures, with some typical case studies from local practice. Well, this presentation is quite long. It's about 80 slides, so I'll separate it in two parts. First part we'll discuss today, and the second part of this topic of this presentation I'll present you next week when it will be a final day of this course. As some introduction to this case study part, where we'll present all the details relating to numerical simulation, the construction sequence, and all the explanations related to few case studies as landslides were involved during the highway construction. First, in first part of today's presentation, I'll show you some main principles and main assumptions used during the numerical calculation that are more or less complex. So first questions that must be answered is what exactly are we modeling when we are trying to simulate some landslide and when trying to simulate interaction between the highway construction elements and moving soil or landslide. Here you can see one typical landslide that is triggered by rainfall after cut slope excavation. So the cut slope was excavated like this, and then a failure occurred all uphill about 100 meters above this excavated part. What you can see on this figure is this man who is absolutely stuck in this liquid soil. But first thing that we must underline and define is the main principle of the theory that is used for the prediction and calculation of some safety and for numerical simulation of the failure like this. The main assumption of for the calculation for that are necessary for the simulation of in some numbers, numerical simulation of this kind of condition, is that the failure did not happen due to the soil consistency change from solid to liquid. If you look at here on the surface, you'll practically see a liquid soil, and that's why people who look at some failed slope, there is some deep-seated failure like here, the first assumption is after some heavy rainfall, the water filtration occurred in this material at some depth of 5, 10, 15 meters, and that soil become liquid due to water moisture and water level increment. Actually, that's not the case. That's not the case. That's not the principle that is used in numerical simulation, in numerical modeling of this kind of scenario. And the influence of water is absolutely different. And the, that this assumption is not appropriate, it can easily be confirmed that when the soil is under pressure, like here, you have some surface, and then we did, for example, excavation here, and then the failure occurred here. So this sliding surface in this practical example is about, I don't know, about 10-meter deep. Let's say 5 to 10-meter deep. That means that you have quite a lot of self weight pressure here where the sliding occurs. When the soil is under this kind of pressure, which is 10 meters uh, with some multiplied by some unit weight of the soil that is about 10. If it's on this submerged condition, then you practically have about 100 kilopascals here at this level. It's practically not possible for soil to become liquid under such a large surcharge pressure. So the theoretical principle used for predicting landslide, numerical simulation of landslides is different, and we'll explain it in the following 2 or 3 slides. We'll show exactly why the water trigger landslide. And it's not because soil becomes liquid after reaching water from solid to liquid. That's not the case. What's exactly the case? It can be illustrated with this very, very simple problem that we showed at the beginning of this course when we in these lectures, when we introduced some stiff block laid on some stiff surface underlying it. So if we are increasing the slope of this surface at one moment, the sliding of this block will occur. Why? Well, that's why, because the combination of this force that is trying to push this, for example, wood block downstairs, it is that force overcoming this resistant force, friction force. This is resistant friction force that is equal to this R multiplied by friction coefficient that is marked F0 here. So we have this perpendicular component multiplied by the friction coefficient, and that's exactly the resistance. If this moving force T is larger and passes the value of this friction force, then the sliding will occur. It can easily be shown on this diagram that relates normal force to this action force that pushes this stiff body to move down the hill. If you have the combination of this T force and N force lying on this red line, while the slope of this line is actually this friction coefficient, that will be the moment of sliding. If the combination of normal force and shear, this moving force, T force, is below this line, then the sliding actually do not occur. And that is for any slope flatter than this one. The combination that marked here is actually not possible, because when the combination of T and N force comes here, the failure occurs. Well, that's exactly what happens in landslide when you don't have some stiff elements like here, but you have slope that is sliding like this. But still you have some element with his self weight, and we have some reaction here. There's a friction force that is supporting the soil mass, and we have the component of this weight is this attack force that's trying to move this landslide down the hill. The question is, where is the water in this theory? Where comes the water? Where it can be recognized very simple, because if you see this component n is actually changing if you have water increment here. For example, if this wood element, stiff wood element, is submerged in water, if it's submerged in water, it will be the its self weight will be reduced. You know that the self weight is reduced due to this submerge force that we usually mark as some U force that pushes this body upstairs, opposite to the force of this self weight. That means that this N force, if it was like this before water, then the resistance was like this, resistance to sliding. But if you now reduce the normal force, the resistance to sliding will be reduced as well. This is really main principles of influence of water on the stability of the soil mass. What is important to see? It is important to see that after you submerge this element to water, there is no change of friction. There is no change of friction coefficient. The only thing that changes is this normal force. That's this component of the self weight. Since it reduces, that's why the resistance reduces. The same thing is happening in the soil mass, because without water you have this self weight, and when the water comes here, this component is reduced. The self weight, actually we call it effective stress. It's called effective stress. That is actually a stress, total stress divided by pore pressure. But we can discuss in stresses, we can discuss in forces. It's absolutely the same, since the stresses multiplied by the surface is exactly the value of this force on this very simple physical model that can be some model for defining something what is happening on the real landslide problem, like shown here. Additionally, of course, if the water is seepage to this fold, there is also additional seepage force. So it should also be introduced when defining the safety factor definition, but we'll show it in some, in the next slide, after we just underline something that we explained in these two previous slides. So we really did see a man stuck in this liquid sandy clay. The question is, why did not the red dotted line changes its slope? Why, after getting the water here, why this line is not like this? If you have some material that is not liquid and now it become liquid, obviously the strength of this material that is not liquid is better than this liquid material. If the material is better, it had better strength parameters, that means that the slope of this line is bigger than before, or this value of cohesion is higher than it was before soil becoming liquid. But as we said here, there is no liquid of the soil when the soil is under surcharge pressure. The liquid can occur only on this free surface where the vertical stress is practically equal to zero, or maybe in first 10 or 20 centimeters, it can become liquid. So this is just a consequence. What we see here is a consequence of some surface erosion where the soil has become liquid. And that is marked here. Only topsoil 10 to 20 centimeter depth reach liquid consistency state. This happened after the failure occurred. Which failure? Well, this failure. This that is actually important failure, which goes about 100 meters higher for the excavation depth in the range of about 10 meters. Of course, the theory we explained, it's not appropriate for the problems like this. That's why we'll said we are not discussing the problems like this. What are these problems? Well, it's, for example, soil suffusion, where the head water is doing the surface erosion at some depth. That's why it's called suffusion, like erosion at some depth. And practically, this in this natural ground, you have the holes like natural pipes that are which diameter is increasing by time, and at some period of time, you have something like this at the surface, something that can be initiate some kind of sliding. Another problem that can occur and is occurring in practice is different kind of chemical weathering, where you have different kind of man-made materials that are used for construction of some embankments, some municipal waste, and similar things. There you can have some chemical processes which can introduce or have some sliding as a consequence that can cause large problems, but that's something different. That's due to some chemical weathering. Also, the third part is this earth flow. Earth flow is actually a surface erosion that uh, that brings the surface material down the hill and causes totally different thing than this deep seated landslide that we are concentrated at and what we are actually discussing about all the time. Well, this is a very important slide if you really want to understand some main aspects, main terms relating the stability analysis, and it is all defined on the one very simple problem of landslide. It is called like a very long, infinitely long landslide. For example, that would be a landslide that is very much longer than its depth. That should be like this. For example, you have a 10 meters deep landslide, and its length is, for example, over 100 meters. There are actually plenty of landslides like this in practice, where you have that here is some bedrock material not prone to sliding, and above it you have some surface material, soil-like material, sandy clay, and, or similar. What usually happens here, as we said in the first presentation of this course, is that this is typical sliding mechanism where you have the water increment, but the water level increase from bottom to the top, since this bedrock material is actually impermeable. It's not possible for water to go down. It's going down the hill and then going to some river down there or something. And very often we have the slidings like this due to water increment, especially if we do some excavation at the bottom here, or we put some additional load up on the hill, and so on. For example, it's very important to know what we we need to know, or what we sometimes know and sometimes don't about the landslide. And that is these four aspects. First, it's soil parameters. For any numerical analysis, for any calculations, we always need the parameters of this material prone to sliding. What we what we still need to know is the groundwater pressure. We explained that the groundwater pressure influence the stability of the slope. More water in the slope means lower safety factors. When there is no water in the slope, usually there is no sliding as well. Third thing, what we sometimes know in advance and sometimes we need to define it, is actually a safety factor. There are some typical conditions like safety factor equal to 1. If we get to the site, to the field, and we see that the sliding occurred like we see it here, so we definitely know that the sliding occurred. Large displacement occurred. There's typical cracks at the top. There is this typical bulge at the bottom on the landslide toe. So the sliding occurs. What we can be sure about this landslide is that the safety factor of this landslide is equal to 1. What does it mean? That means that the resistant forces are equal to this moving forces that tend to push this slope down the hill. So the safety factor is exactly the ratio of the resistant forces and this moving, disturbing forces that are trying to push the soil down the hill. Additionally, we can have some monitoring results. The monitoring results can bring us the information of safety factor as well. If some displacement were measured, maybe we don't see this on the some location at the field. We don't need to see such a large cracks that show us that obviously the sliding occurs. It can even be no surface indication of sliding, but for example, if we install an inclinometer here, the inclinometer results should recognize this initiation of the sliding, even if it's displacements of 1 centimeter or 2 centimeters. So when there is no indication that sliding occurred, when you look the surface, you can catch this displacement on the precise measurements like some geodetic survey or monitoring results, and that is very useful data. So then we know that the sliding is about to happen, the large displacement is about to happen, and we already know that the safety factor is actually equal to 1. This is very important. This is very important to know that the safety factors must be equal to 1 where the sliding occurred or it's about to occur during the according to monitoring results. Why it is important? Well, that's important because when we are sure that safety factor is 1, then we can recheck the parameters we are using in the numerical analysis. What that mean? We can take the sample of this material. We can now do here a borehole or from the surface do some sampling, and we can bring samples to laboratory. Then in laboratory, we can get the results like cohesion equal to 5 kilopascals, for example, and internal friction angle equal to 22 degrees. What we additionally need is the groundwater level. Groundwater level. We rarely know the groundwater level in some landslide at the moment of sliding. You see, for example, like here, the contractor performed this excavation. There is no piezometer up the hill. There is no continuous monitoring of water level up the hill. And this failure occurs, and we are not sure what's the water level. After that, we can do the borehole and measure the water level in period maybe 7 to 15 days after this sliding occurs. But we are not sure that the groundwater level 10 days after is same as the groundwater level at the moment of sliding. So that's additional unknown thing. We are not sure about groundwater level. That's why it's very helpful if we really know the safety factor. What we can do then, we can combine parameters from the laboratory with the groundwater level to get the safety factor equal to 1. Well, that's called back analysis. That is called back analysis, back numerical analysis. So we are trying to confirm the conditions on the field, and that is failure, and that is safety factor 1. Very often, due to sample disturbance, the parameters get in the laboratory, and any groundwater level cannot bring us to this factor of safety equal to 1. That's due to disturbance of the sample, which are always disturbed at more or less. It can bring us that problem as well. That's why we sometimes we also fix the cohesion value. We can also fix the groundwater level near the top of the slope, since we know if the failure occurs after heavy rainfall, it's possible that the water level are very high. And then we are searching for this phi value. We are searching for the phi value to get the safety factor equal to 1. That's also back analysis. In back analysis, we are We are searching for the appropriate parameters and groundwater level. We are searching for it since we are not sure, but we are sure that safety factor is equal to 1. And what we also must be sure is that after remediation, after drainages, retaining walls, anchored walls, and so on, we need to bring this safety factor from 1 to some value over the 1.3, 1.25, depending on the code, the standard that we are using. The equation for the safety factor can easily be defined if you use the original definition of safety factor, and that is resistance divided by moving forces that try to push the soil down the hill. For example, it's the easiest way to explain here. The safety factor here is actually the ratio of resisting force. It's F friction divided by T force, where friction force is actually this reaction normal force multiplied by friction. The same thing occurs in the soil, but we don't have the friction coefficient. We have tangents of internal friction angle. Additionally, we can have a cohesion in soil. The cohesive soil, like clays, silt, can have a cohesion value. The cohesion value is actually like you stick this wood with the concrete. If you do some glue and stick this to this, you will have some resistance even without this self weight of this block. That means you can push it vertically and it will still stand like this if this cohesion is higher than the value of the self weight of this block. That's what we have in the soil. Numerically, it can be defined like this. If this is N force, this is T force, the slope of this is F0, and this is cohesion. Of course, since this is force, this will be some measure of cohesion, since cohesion uh, SI unit is kilopascal. So this is resistance. Resistance to sliding when the N force equals 0. The soil has some resistance even without normal soil, only cohesive soil. The sand and the gravel do not have it. There is no resistance to shear of sandy material if you don't press it. For example, if you have some slope in the sand, you just push it like here and you'll fail it. But if you press it from here, you'll have a lot more effort to do the shearing through this sandy material. So this is a very simple equation that can be defined after this. When you divide the resistance with moving forces, we get to the result like this. What you can see, the higher the cohesion value, the higher the tangents phi value, internal friction angle, the higher the safety factor. Of course, the higher the strength parameters, the soil is more strong, and it can resist to sliding better than some low strength soil, and the safety factor increases. What is also important is to show in this equation what happens when the water gets to the soil mass. When you have water seepage on some slope, so this is infinitely long slope, this is some bedrock soil not prone to sliding. What happened here at the bottom of this soil material, if we have water in the slope, is that we have some pore pressure here. We have pore pressure at the bottom of this. What's the pore pressure? Where the pore pressure can be defined after you draw the flow net for this problem. The flow net consists of these flow lines. That's the line of water flowing. So water flows from this point to this point, from the points with higher potential energy to the lower potential energy. Perpendicular to this line can be defined these equipotential lines. The equipotential lines are actually the line of the same potential as defined by Bernoulli's equation, and this flow net is actually a solution of Laplace equation of water flow through soil. If we recognize this equipotential line, that the potential here must be same as here. So that's exactly what the definition of the equipotential line. That means that at any point along this line, the potential is equal. If we know the potential here, since we assume that the flow line is at the top and the water level is the top of this hill. So the same potential must be here. So then we can draw this horizontal line, and this is actually the level where the water head will be defined if we put the piezometer at the bottom of this element. Anyway, when we define the same this equation, including the water pressure at the bottom, as we said for this block-to-block sliding, the increment in pore pressure will actually reduce the normal stress at this sliding plane. The reduction of normal stress will cause the reduction of this reaction force, and that's the reason why the resistance will be lower in comparison to the condition where there is no water pressure. What is the difference between the equation for the safety factor without water and with water is actually a part here. The second part of this equation will introduce here a ratio that is submerged unit weight divided by saturated unit weight. And then everything multiplied by tangents phi divided by tangents beta, where beta is a slope angle. Beta is the slope angle, tangents phi is the internal friction angle. This ratio is in the range of 0.5. And that actually means that the value of safety factor is reduced by double if there is no water in comparison to the conditions when it's reduced by double for the case with the water in comparison with the condition when there is no water. So if you have dry slope and saturated slope with water seepage down the hill, the safety factor will be reduced by double. That means if you had a safety factor without water equal to 0.2, after the water, that means submerged safety factor will be 1.0. So you were quite safe from the failure before the water reaches slope, and after the water you have the value at the verge of failure. If you look at this also can be analyzed by simple physical models. If we say the material do not have cohesion, C equals 0, all this part of the equation becomes 0. And we only have tangents phi divided by tangents beta, where the beta is angle of the slope. That means if you have some slope that is in slope angle 20 degrees, and you know that it's sandy material with cohesion equals 0, that definitely means, and for example, stable slope, there is no sliding on that slope, you are definitely sure that the internal friction angle of this material involved here is over 20 degrees because it's stable slope. And you definitely know that there is no chance that the internal friction angle is lower than 20 degrees. In that case, that hill would not be stable. It would just be moving. It would be moving down the hill. Okay, this slide shows us all the phases of the modeling. Because when we are doing modeling, there's it's not only the numerical modeling and input parameters, because some conditions from the field first had to be modeled by engineering geological modeling. And this is surface line that we see here. But above that, we have some different kind of materials, different layers of materials, and these materials need to be modeled and recognized by some engineering geological inspection of the boreholes. For example, here is borehole 1, borehole 2, borehole 3. We have 3 boreholes in this cross section, we may have some monitoring results, and we may recognize some potential surface line, failure line that is located here. After that, we are defining this numerical model, some simplified geotechnical model, which introduces this bedrock material and this topsoil material, and it also needs the input of the groundwater level. As we said, it's very important to define the appropriate groundwater level that is usually unknown at the moment of sliding. That's why we need back analysis. And for any landslide, we know that the safety factor is equal 1. And then we are doing different combination of input parameters, friction angle cohesion, ground water level. Different combination of these elements can bring us to factor of safety equal to 1. It is also very important to note when we are on safe side and when we are far from safe side when adapting the groundwater level. It's suggested that the groundwater level should never be at the top of the hill, at the top of the surface in the back analyze. Why? Because if we introduce, for example, drainages like some remediation measure, for example, drainage is constructed here, after the drainage will probably reduce the water level for a very large depth. And then the safety factor from 1 will bring to a very high value, over 1, very much above 1. But what if the moment of failure groundwater was here? Then this drainage will reduce the groundwater level only from 1 meter. The less we reduce the groundwater, the less we influence on the safety factor, and the less is the increment of the safety factor from 1 to something above 1. That's why this groundwater level is usually at the 1.5 or 1 half or 1/3 of the landslide height of this, actually, let's say vertically measured depth of the landslide. So the groundwater should be at the middle of the landslide depth or even at the lower third part of this level if we are not sure and if we don't have information of the groundwater level at the moment of sliding. But we usually do not know that. We usually don't know that because we are not measuring pore pressures at the moment of sliding. We usually measure it after the sliding occurred. 5-7 days when everything settles down, we are doing boreholes and putting piezometers in the slope, and we measure the pore water pressure in the following period. But at the moment of sliding, the water level could be different from that what we measure after. Okay, we are about to finish this first part. If you have some question, you can ask. Maybe to clarify this. If there is no question, we can continue in, for example, 5 minutes. That's 14:45. And in 5 minutes, we can continue with this second part of today's presentation.